Proof is easy and nice. Well, I'll just produce contraction. So we have G, which is star shaped, centered at 0. Now I need to produce a map contracting homotopy G cross 0, 1 to G. And I'll do it by the following formula. So we have Z node, and we have Z. And all this straight line is inside G. So it's clear that we should just walk along this straight line from Z to Z node with a given speed. So formally speaking, H of Z C equals, Z node plus Z minus Z node. So this times 1 minus T. So definitely it's a continuous function on G cross 0, 1 with values in Z. And if we evaluate it at T equal to 0, then of course we get Z. And H of Z1. So this will vanish, but it will give Z node. So somehow this book is not about topology, so being simply connected, which is important property in view of the theorem which I'll formulate very soon, is something we cannot measure or verify, but some subset being star-shaped is easily verified, because if it is, then you can write the formula. If it is not, you cannot. So, well, definitely say a disk is star-shaped, right? Because there are smaller and smaller disks around the center. Good. So now we come to the crucial part of the lecture, formulation of Cauchy theorem in full generality. So formulation. Theorem. Well, there are many Cauchy theorems here, so this is called Cauchy integral theorem. So let G and C be a simply connected domain. And F is such so it's a function of G which is holomorphic. In V. So differentiable, complex differentiable. Such that the integral over gamma of F is 0 for any loop gamma. So corollary from this is that in view of what we discussed at the previous lecture, f has a primitive. Right? So the statement is that if we have a simply connected domain and a holomorphic function, then every integral over a closed loop is equal to 0. And corollary. Thus, by the previous lecture, f has a primitive. So let me, before starting the proof, so we will not prove it in this generality. We will prove it for star-shaped domains. But let me give an example showing that this condition of simply connectedness is important. So example, and then we'll start the proof. So suppose that our G is just complex numbers without 0. So it's a nice domain. And our function f of z is 1 over z. Then, well, it's certainly, is it holomorphic? Is it holomorphic in this? So, is it defined in G? Definitely it is. We can take inverse of any non-zero complex number. Is it holomorphic there? Yes, it is. Because, well, we can differentiate it, and the answer is like in the real domain. So it's 1 minus 1 over z squared. No problem with differentiation. However, you got a home exercise, or whatever, exercise to think about. I think it's 2-2. Yeah, 2-2. That basically tells you that the integral of dz over z, so of this function, over paths gamma which wind around 0, so like this, are certainly non-zero. And moreover, if you do it like this, or you do it like this, you'll start getting different answers. So the answer depends on how many times you go around 0. So how do these facts agree with Cauchy theorem? It's a question to you.
The domain is not simply connected.
Yes, the domain is not simply connected. And actually we'll find, so the reason G is not simply connected. Now how to improve the situation? We'll replace G by G prime, or maybe G tilde, which looks like this. It's still complex plane, but we make a cut from 0 to infinity along the real line, like this. Now, what about this domain? Is it simply connected? We had a lemma about this. Yeah.
So I guess it's actually star-shaped.
It's star-shaped. Yeah, you can put your base point somewhere here on the horizontal line, on the real line, but in the negative part is at 0. Then any other point no matter where it is connected by a line with this point. So it's contractible and so simply connected. Since it's simply connected, no matter which loop you take here, the integral will be 0. So for any gamma from 0, 1 to g tilde, which is smaller than g, the integral of dz over z over gamma is 0. So if you notice, I drew loops around 0 here, so none of them will be allowed because my cut actually cuts all of them. So these loops which produce a contradiction will not be the ones we consider. Good. This will be important in the future. Now let's at least start the proof of Cauchy theorem. So remark, we will prove Cauchy theorem, integral theorem, for star-shaped domains. Great. Let's actually do it. And this main technical tool in the proof, main technical or analytic tool in the proof. So this is our next step. It's the Gorsas level. It states the following. So we have a domain G, and F is holomorphic in G, and delta inside G is a solid triangle. So it means that there, where G is like this, and then there are 3 points, and the whole triangle between them is inside G. So then it follows that the integral over, well, the boundary of this triangle, which I'll denote like this, of f is 0. Okay. So this is the formulation of the theorem, of the lemma, and actually it covers basically the proof of the theorem. Let me prove it. So the idea is that we keep subdividing and recalculating. That's proof of the lemma. So we have this big solid triangle. And let's say that we oriented it so we know how we go around it. So let's say like this. So our path starts here and then goes in the direction of this. So let's denote by I the number, the complex number, which is the integral over of f. Now subdivide let's just take the centers of these intervals, connect them. We'll get 4 triangles. Now notice I will not even write this, but so I will write the final conclusion. So we're integrating like this, but we can also integrate like this. So we go around this one. Then we go around this one, but this goes in this direction. Then we go around this one. Then we go around this one. So notice that if we take these 4 integrals around these 4 closed paths, then these sides will cancel out, because once we go with one orientation and second time we go with the second orientation. Okay? So the whole integral I will be the sum of I1, I2, I3, and I4. So the integral is sum so yeah, do I have a special notation for these triangles? Yeah, so I'll call them so I is integral of very good. So we assume that I is not 0, and then absolute value of I is not 0. So take one of these. So take one of these integrals. There exists a triangle. Small, so a subtriangle, one of the 4, call it delta 1, such that the absolute value of the integral along it is greater or equal than 1/4 of I. That's clear, because otherwise triangle inequality will fail. So if all of them are less or equal, then we'll get a contradiction. Okay? So otherwise we contradict with triangle inequality. I mean, for absolute value. Okay, now we'll proceed. So now write I1. Maybe it's a bad notation here. Maybe I should I here. So I1 is integral over this the boundary of delta 1 of f. So now repeat. Now with the same picture. Now this triangle is our I1. Okay? So subdivide again. So find. So this now was our I1. So delta 1. Again subdivided, and repeat this consideration. One of the 4 will have the same property. So find 2, so one of the 4 subtriangle, such that the integral over d delta 2 of f by absolute value is greater or equal than absolute value of I1 over 4. Then it's greater or equal than I over 4 squared. And continue. So at every step, you have the previous triangle, and then you divide it into 4 triangles, and say that the integral over the previous one is the sum of 4 integrals, and find at least one of them, and fix it, so that the inequality that we're taking more than 1/4 part of the integral by absolute value is satisfied. So we'll get this sequence of triangles, delta containing delta 1, containing delta 2, containing so on, and getting smaller and smaller with absolute value of integral over d delta n of f. So the way I wrote it, it's greater or equal than 1 over 4 to n plus 1. So of course we plan to come to contradiction. Now notice that here. So notice that sides of delta n are 1 over what? 2 to the n, I guess. Maybe 2n plus 1. Of sides of original triangle. So in particular, the perimeter so L n, which is L of delta n, just the length of this path, is 1 over 2 to n plus 1 L, which is L of delta. And in fact, so we have this shrinking set of subsets of complex plane, and they get smaller and smaller. And the intersection of delta I, of course, is just 1 point. Just 1 point. And the reason is you can take a random point zi inside delta I, then by these considerations with the sides and with the perimeter, we get that the sequence Zn is a Cauchy sequence. In complex numbers, so then there's a unique complex number which is the limit. Okay, so comes the analytic part. So the analytic part goes like this. We have this Z node. Choose a disk, so R, such that for Z minus Z node less than R, so since the function is differentiable, we can write is less than so we can do this because f is differentiable. At Z. So let's draw another picture about this. So starting from some point, our triangles will be inside this disk. So let's do it. So this Z node, there's this K Z node R, and starting from some point, the triangles will be like this. This is our triangle, one of them, so delta n for example. Yeah. And as we calculated, I think that my enumeration differs from the one in the book. And we have that the perimeter L of delta n is 1 of 2 n plus 1 L of delta, which is 1, 2, n plus 1 L. So that's what I wrote before. I think the book says 1 over 2 to the n, but I think it's not important. Now, if we look at a point here, so this is our Z. After all, we'll be integrating. So we are interested in this distance, and so for any point on the side, we can estimate this distance by, so for Z in so it's a calculation inside this triangle that this distance is less or equal, so it can be estimated by the perimeter. So the book says that it's estimated by 1/2 of the perimeter. And this is 1 to 2 and plus 2 L. Okay. So now we want to estimate the integral. So we want to estimate the integral. And we do it like this. So remark. So we can consider additional function in the linear polynomial. Z goes to f of z naught plus prime of z naught z minus z naught. So since it's a linear polynomial, it has a primitive, and so its own integral is 0. I mean, the function depends on z, and z naught is fixed, so it's just a linear expression. So it follows that we can replace by okay. So but we are interested in the absolute value. So let me add absolute values to both expressions. And then there's a way to estimate. So the estimate comes from the estimate on the function, on the absolute value on the function inside, and the length of the curve. So then this is less or equal. Then, so the estimate on the function inside gives us and the length gives us L of delta n. Very good. Now this, by our calculations, is less or equal than epsilon times, so distance between z and z naught was estimated by 1/2 of L of delta n. And then there's L of delta n here. Yeah. So now let me continue this calculation. This is basically the most technical part. So again, looking at this formula, one factor L of delta n comes from the perimeter, the length of the curve we're integrating over, and the other factor comes from the estimate on this function, of the absolute value of this function. So the point is that that we get that this is equal to, I'm continuing from here, equal to epsilon times 1/2 L of delta n squared. And we remember that L of delta n was the original perimeter divided by 2, I wrote n plus 1 squared. So this is 1/8, I guess, epsilon 1/4 to the n, and then L squared. Now we substitute it into the inequality we started from. So the integral we're interested in was less or equal than 4 to the n integrals, or maybe it was 4 to n plus 1. And this was less or equal than, so 4 to the n cancels out. So the important is that epsilon, the important thing is that epsilon was chosen randomly small. So, yeah. So the 4 to the n cancels out. We get 1/2 epsilon L squared for any epsilon greater than 0. Yeah, so we come to contradiction because we started from assumption that the integral is not 0. So thus, equals 0. And of course, I can erase epsilon 0. Good. So we will keep this in mind, and I'll probably just formulate the actual theorem I was supposed to prove, but the proof will be on Monday. I don't want to hurry. So, application of the lemma. So, I'll call it a proposition. So let's say, let's choose G to be a star-shaped domain. F is holomorphic G. And gamma is the staircase type curve, closed curve. So staircase loop in G. So then the integral of the gamma of f is 0. So as you see, it's weaker in 2 assumptions than the actual theorem, but one condition can be dealt with, but the other one so yeah, so the picture is like this. We have this star-shaped area, and then our curve is something like this. And it's closed. And then the integral is 0. Yeah, the idea, I'll tell you the idea, but the actual proof will be on Tuesday. So we are good with triangles. Yeah, so we can integrate over every triangle and get 0. Now you just cut the interior of this curve into triangles, into solid triangles. So I'll draw a picture and then to illustrate everything, I think. So I just connect, say, vertices with some point with the yeah. So what I drew was not star shaped actually. So from here I don't see this. So to make it star shaped, I need something like this. Now it's clear. So I cut it into triangles. By the definition of star-shaped, all these sides are inside and the interiors are also inside. So then integration over this thing is the sum of integrals, so I just orient it from the very beginning, like we did with the triangle. So there are outer sides of these triangles and there are inner sides. And every inner side can be, so is counted twice. One in this side of this interval and one in this side. So we'll get that the integral over the whole curve is the sum of integrals over these triangles, and for triangles we have the previous lemma, which tells us that the integral is 0. Okay? So it's the idea of the proof, not the proof. So we cut, we integrate over triangles instead of integrating over the staircase curve, and every summand gives us 0, so the sum is also 0. Good. So I owe you this from this section.